Okay, so hi everyone. Welcome to this week's South American Geometry webinar. Today we have Yang-Hui from a number of institutions, most centrally University of Oxford and the London Institute of Mathematical Sciences. Yang is quite a bit of a pioneer in terms of bringing in machine learning and sort of AI perspective into theoretical physics and but tangentially also into pure mathematics. Uh, his recent and ever expanding work on Calabi-Yau threefolds and machine learning, the Calabi-Yau landscape, has been quite commented recently, and he was kind enough to accept giving us a panorama of how he sees machine learning, mathematical structures today. Is going to tell us about universes as big data. So Yang, the floor is yours. If you can maybe manage 50 minutes plus questions.
Yep.
Cool, please go ahead. Oh, I'm so sorry. I have to say this. It's a word from our sponsors. So if you wish to join our WhatsApp group, which is exclusively for announcements of the talks, you can follow the instructions on the chat. There's also an email mailing list. You just have to send the word webinar to the email provided at unicamp.br. You can also check our calendar of upcoming talks as well as previously recorded talks on our YouTube channel. And should you wish to add this recurrent event to your Google Agenda, you can just follow the link, the very long link, ridiculously long link provided as well, right? So you can keep in touch with us in all of these ways. So now, without further ado, Yang, please go ahead.
Yeah. Thank you very much, Enrique, for this kind invitation. And I wish this was in person because I've never been to Brazil before. So maybe someday.
Time will come.
I will. So thank you. So I'm going to talk about some of the explorations of machine learning to pure mathematics, but through my original motivation, which is through mathematical physics and string theory. So I don't think I need to emphasize this fact that it's been known for at least a century that algebraic and differential geometry and topology, in any combinations of these words, and representation theory is the right language for physics. So, for example, if you talk about gravity, you should think about Ricci two forms of tangent bundles. What is an elementary particle? It's an irreducible representation of the Lorentz group, and so on and so forth. If anything, string theory is really a brainchild of this gauge gravity geometrization paradigm. Okay, so this has been known since at least Einstein. But what I want to emphasize is that no, that was 100 years ago. But in this dawn of the 21st century, this is a new exciting era where mathematicians and physicists not only talk to each other, but they're beginning to talk to data scientists. And this has really been a development only in the last 10 years or so. And you can already feel this in the pure math community. The SAGE project, the Macaulay 2 project, the GAP, and all these projects are showing up only in the last 10 years or so to be indispensable tools for mathematicians and physicists. So I'm just going to give this one slide overview of what originally motivated me into doing this problem. And it's that there's this indisputable equation from string theory, and that's the fact that 10 is equal to 4 times plus 3 times 2. What this equation means is that string theory is a theory of quantum gravity that lives in 10 dimensions, and we live in 4 dimensions. So somehow we have to geometrize away 6 extra dimensions. And the traditional solution of that is to take these 6 extra dimensions to be a complex scalar manifold for reasons of particle physics, and in particular to take a standard solution is to take that to be a complex scalar manifold with Ricci flat curvature. So in other words, a Calabi-Yau manifold. So that's how Calabi-Yau came into the world of physics. But I won't really talk much about that in this talk. What I really want to emphasize that what got physicists going in this whole dialogue is the fact that the geometry of this extra 6 dimensions determine universes. And there are different universes. And you can translate the properties of these universes to properties of geometry. So for example, a particle and their interaction in this 4 dimensions can be determined by cohomological theories on these manifolds, and etc., etc. Which I think is a very beautiful and cute answer, in some sense, to this old saying of Kepler that where there is matter, there is geometry. But you see, then we raise this problem because each geometry produces a 4-dimensional universe. What is the right philosophy of approaching this? Is our universe probabilistic? Is it anthropic? Is there some kind of selection rule that says that our universe is special? Or are we just one of the possible multiverses that produces from this theory of everything? There's no consensus in the physics community as to which is which, but it's food for thought. But what I like to point out is that this search that this community has been doing for the last 10 years is very much in parallel to the exoplanet search. The NASA's exoplanet habitable zone search program, which has produced something like 1,000 Earth-like planets in a scan for something like 10 to the 10 possible galaxies, is very much like what we're doing here, except NASA is looking for planets that are like us. And what string theorists are doing now is to look for universes that are like us. But with this comes this big problem, which is called the problem of vacuum degeneracy, and which is considered the biggest theoretical challenge to string theory. How do you select, what is the sample size of your selection? Well, there are a lot. So the first person to ever think about this problem is called the statistics of string vacuoles. It was Mike Douglas in 2003, and then various more recent papers of KKLT and Taylor, so we're talking about numbers of this size. Right. So these numbers come from simple estimates of the number of algebraic cycles on a typical Clavier manifold, threefold, that can be constructed. And then if you put extra things like bundle structure, you get into around about this range. Now, you may ask as a pure mathematician, why are these numbers so big? So a simple illustration will show you. Because the reason for it is since this is a geometry seminar, so this is the end of physics I'm going to talk about. So there will be no more mention of physics. So because we've boiled everything down to a problem in geometry. The basic reason is actually very simple. Algebraic geometry typically leads to combinatorial geometry. And once you're in the world of combinatorics, you're completely sunk because you end up with exponential growth kind of problems. So let's take my favorite example, which is the following question. So first of all, let me define for you what a reflexive polytope is. So a reflexive polytope is it's a polytope, so a convex body in Rn, simple Rn, such that there is a single interior lattice point, and all of the vertices are lattice points in Rn, and all of the bounding facets are at distance 1 from this internal point. So it's a very simple combinatorial definition. So you can easily show that this definition, from this definition, you can prove there's a finite number of reflexive polytopes in each dimension up to GLNZ, or take SLNZ is enough. So let's take an example. In dimension 2, you can clearly see up to SL2Z, there are 16 such objects. So these are convex lattice polygons such that each vertex is a lattice point such that there's a single interior point, which I've marked in green, and such that all of the bounding facets is lattice distance 1 from this interior point. So this was already known to the Italian school of algebraic geometry in the 1890s. So these are called Fano polygons. Fano, Del Pezzo, these people are from the 1890s. So So why do physicists care about this? It's because of this beautiful theorem of Borisov and Batyrov in late 90s, which says that if you have such a combinatorial object, you can create a compact, not necessarily smooth, toric variety. And you take this toric variety and take the anti-canonical divisor. That anti-canonical divisor is Calabi-Yau. So this is a very systematic way of constructing explicitly a Calabi-Yau manifold. So in dimension 2, you can create from these polygons, these lattice polygons, a two-dimensional toric variety, which are called funnel variety, or funnel surfaces. And then if you take the anti-canonical divisor in that, you have a Calabi-Yau one-fold as a hypersurface. And that Calabi-Yau one-fold, we know, is just simply an elliptic curve. So because it's richly flat. So we know there's 16 of this. So the question is now, what about you just go one dimension up? So three-dimensional lattice polytopes with this property. Yeah.
Yeah. So for the benefit of everyone, can you try and sort of give an idea of how we get the Calabi-Yau from this combinatorial data? Just sort of a bit more.
Yeah, sure. So, I mean, the equation is actually explicit. So what you do is you take one of these, you take the vertex data from this, you find the dual polytope, and then from the dual polytope, you can write down the explicit direct. So once you have the polytope, you have the vertex information, and you just raise the number of variables to this thing, so like a Newton polytope construction, and that defines you for a polynomial, and that the vanishing locus of that polynomial in that toric variety is always guaranteed to be Calabi-Yau because of the Borisov-Batyrov theorem.
And what about the weights?
Yeah, good. So in this one, so in this case, we don't, because all weighted projective spaces are toric varieties. So we don't even, it's even more general. So we don't have to worry about the weights. So here the construction is you just really literally write down the Newton polynomial as a vanishing hypersurface written into the toric variety. But it has to be a vanishing locus in the toric variety. The toric variety itself can be written with weights if you want to embed that into with some polarization into PN. But so you only have to really worry about the weights if you're embedding all of this into PN.
Cool, thank you.
So it's very nice. At the end of the day, if you give me one of this, you have the full combinatorial data to just write down the vanishing polynomial locus. So it's very explicit. But the problem is, there's 16 of this in dimension 2 that was known to funnel. Already in dimension 3, nobody had any idea what it's up to SL3. So this had to wait 100 years for two physicists, Kreutzer and Skarka, with the development of computing to actually just enumerate it. So they wrote some very clever algorithm to piece together what is the three-dimensional versions of this. And they count it up and you get this number. But if you do this in dimension 3, you take the hypersurface, you get a Calabi-Yau two-fold, which is a K3 surface, which is not that useful for constructing four-dimensional universes. So Kreutzer Skarka did even more. They spent one more year to run on a Pentium machine at the turn of the century to construct the next number. And this number is astronomical by the 20th century technology standards. This came to 500 million. So you see that this growth is clearly exponential. And we don't know what the number is. We don't even have a generating formula of any type to even count what the next number is. But whatever it is clearly in the trillions, because you can just plot to see what the next number might be. So this is just an illustration why we get such huge numbers when we're talking about constructing vacuum for string theory. But this is just a problem in algebraic geometry. If you even such a simple problem of constructing Calabi-Yau, this is just one way to construct Calabi-Yaus. It's certainly not true that all Calabi-Yaus can be constructed this way. Even a very nice concrete family like this of constructing Calabi-Yaus as hypersurface and toric varieties, you are led to numbers like 500 million very, very quickly. So this is why we have this problem. So so this got me thinking, well, well, if you have numbers like this, what do? Well, you talk to data scientists. And for data scientists, apparently they're not afraid of numbers this big. So this is how I got into this, and also some independent groups who are friends of mine also got into this. Around about in 2017, we started thinking, well, if you got numbers this big, 500 million or potentially 10 to the 500, there's just no way to even enumerate the data. I mean, think about this, right? You get one of these manifolds, you're going to compute its cohomology, and then you put some bundles on this and compute the bundle cohomology, and then you're going to do all the sophisticated topological computation. It is just no longer possible. So, is it possible to get machine learning involved to try to solve this problem? So that's what originally motivated me to think about this problem. So, and the answer, surprisingly, is yes. And I'm going to give you a very concrete example. So, I've said this in front of many algebraic geometers, and I'm still alive. They haven't killed me, which is a good sign. And I'm just making this proposal that algebraic geometry, at its core, is an image processing problem. So let me illustrate what do I mean by this. So I'm going to give you a typical configuration of Calabi-Yau manifold. You don't worry about what this manifold comes from. This could be vertex data, for example, of one of these reflexive polytopes. It could be embeddings of multi-degrees of polynomials in some projective space. And what do we normally do when we say that a certain Hodge number of this Calabi-Yau is 22? Well, Bourbaki has taught us well. We chase sequences until we can't do this anymore. So you do the standard. You do some standard embedding. You put this in some you do the standard Euler sequence. You induce the Euler sequence in the long exact homology, and that's what you compute. What you normally would do to compute Euler number or to compute Hodge number or any Betti number. But the problem with this approach, which, by the way, the good thing is that everything that we're familiar with in the algebraic geometry community, all of this has been actually implemented into Sage, and in particular into Macaulay 2. Macaulay 2 should, in principle, do all of this. And yes, you can do it. But the problem with algebraic geometry, computational algebraic geometry, is that whenever you're given systems of polynomials, the first thing you need to do is to put in Grobner basis. The Grobner basis, unlike Gaussian elimination, which it generalizes for linear systems, is a double exponential complexity problem. Gaussian elimination is polynomial time, but Grobner basis is not. It's double exponential. So you're very quickly sunk. You're stuck with the same problem, like counting numbers like this. So we're talking about astronomical numbers, for each of which we have a double exponential complexity problem. So traditional methods is just simply not efficient enough to do what we want to do. So then it got me thinking about this problem is that, well, maybe how about think about algebraic varieties not as matrices, but as images. Well, I mean, of course, I'm using images to be cute. You don't have to think about images. Image processing is, at the end of the day, fundamentally, it's just a tensor processing problem. So, but the idea is that this computation using, exact sequence chasing from a configuration like this to the number 22 really should be thought of as the identification problem of this image with the number 22. And now we're suddenly in the world where we're familiar with, how does Google know your handwriting? It's just associating images like this to numbers. So what does machine learning tell us to do? Is to, well, you want to, if you want to identify these digits, that's by setting up a bijection from these digits to these actual digits. And so what Google does is to take a large database where you have sampled such cases. There's some poor graduate students who've been doing this for hundreds of man hours since the 1960s. NIST, the National Institute for Standards, have been doing exactly the sort of thing. They label this, and then you put in through some deep neural network and try to see how your neural network learns such data, and then try to extrapolate. That's all. That's all supervised machine learning is. It's just a very fancy regression of problems of this type. And the reason that machine learning, at least in supervised machine learning, works is because we're guaranteed by such universal approximation theorems. I'm not going to bore you with the details of such theorems. The point is that these theorems are the analog of Taylor's theorem for smooth functions. We know that Taylor's theorem guarantees that smooth functions can be approximated by increasing degree polynomials. But when your function is much more complicated, when it's like a function that tries to map a tensor that represents this picture, or when your function is trying to encode long exact sequences of homology, you don't have smooth functions, but you have much more layers of complicated functions. And the neural network universal approximation theorem says that this is actually doable. So that's all you need to know about machine learning. So that's great. And well, does it actually work? Right? So surprisingly that it does. And initially I was just trying to train this on a few thousand cases, identifying this. And then many authors like Urban and many people in the string community have really shown that you can really calculate this number to like 99.9% accuracy. What you do is you sample a fraction of this data, and you can validate against things that are computed with very fancy, sequence chasing, and then you check, right? You can see the validation accuracies. So this is very nice. I'm very happy that I'm actually working on similar ideas of this with Enrique on more generalized geometries. So this is how we became friends, which is very nice. But this actually got me more thinking more. So this is I'm not going to talk about string theory and algebraic geometry in this context anymore. What got me thinking? Well, if it works so well for algebraic geometry, does it work for other branches of mathematics? Right, so that got me thinking a little more. So this is a review that I wrote a couple of years ago. So let's start with some experimentation. So this is why, I started the title of the talk is Universes is Big Data. That was before. And then the tagline is, can we actually machine learn mathematics itself? Well, so here's an experiment we can all play with. If I give you a sequence like this, you can probably tell me what the next number is, right? I think everybody can say immediately the next number is going to be 0. And then you're going to be right, because this is the multiple of 3 or not. What about this one? Well, since this is a Zoom talk, I can't see the expressions on your faces, but I'm going to give you 10 seconds. Anybody?
Zero.
Why?
Because it goes 101 and then 1001, 1001. Separated by a 0, and then there should be like 3 zeros.
That's a good, maybe. So what this actually is whether the sequence of odd integers is prime or not. But your guess is good. I think I should have included more data. So it shows that you need more data. You need to struggle a little bit, right? Okay, so this is you have to think about it. You can't really immediately pick this out. What about the next one? Of course, I should have given you more data. This is a little more random. Okay, so the next one, it's really hard to tell, and I want to show you that really is very difficult to guess what the next number is. So what this next sequence is the Liouville lambda function. The number of even or odd is the parity of the prime factors to the integers up to multiplicity. Okay, and this is very hard to try to guess. Now, this is easy. This is kind of hard. This is extremely hard. Is it true that a machine learning exercise would also have this layer of stratification of being, of recognizing what difficulty is? So, well, let's try to normalize in some sense in this exploration. So how do I turn this into a machine learning problem? There are many ways to do it. One way I can do it is to have a sliding window. So these are all binary. I've made it all binary. You don't have to, of course. You don't have to have binary integers, binary vectors. But I've normalized this to a binary classification of binary vectors. This is as simple a problem and as normalized as a problem you could get. And then what you do is you take a window, say length 100, and you try to predict your next number, exactly like what Enrique was trying to do, trying to see like this, what's the next one. So then your data becomes a labeled data set of binary vectors labeled by binary numbers. So then what you do, you pass through your favorite classifiers, your supported vector machine based classifier, and there's a whole bunch of like buzzwords in the machine learning community. Your neural network of your favorite form, your grandmother's kitchen sink, whatever, just pass such data through it and try to do this classification problem. Now, interestingly, if you do this, then you take, say, 50,000. Your laptops are so good now because of its GPUs. Taking 100,000 samples of this, it would just take a couple of minutes. And then what's called cross-validation means that you take 20%, say, for example, you train it on 20%, and then you validate against the 80% you've never seen. This is to avoid overfitting. Otherwise, there's so many parameters, you have no idea what's going on. And then you try to record the precision in this cross-validation. And I also try to do what's called an MCC. It's called a Matthews correlation coefficient. What really is just the chi-square. It's a chi-square test of such classification. It's chi-square because you have a discrete classification problem. So you can very quickly convince yourself, if I train this on this data, within 3 seconds you'll get 100%. So because it's a linear transform, so if your neural network has any linear transformation layer, it'll instantly recognize what the next number is. That's great. The prime number gets about 80% accuracy. I have no idea why it does. It's not random, but it's a bit, it's a bit impressive that that at some level your neural network is essentially doing some SIF method, which is what we normally would do in the most naive attempt to try to recognize whether the number is prime or not. And this one, it just couldn't break even. So when you get like 50, when you have 50% accuracy in a binary classification, that means you're doing complete coin toss, right? 50% right, 50% wrong. And that's fortified by the fact that chi-square is 0.00. That means it's complete uncorrelated. You want both numbers to be close to 1 to show you that you're doing a good classification, right? So this is the kind of experiments we've been doing, which is kind of fun. And so then with this idea, so there's a lot of data like this out there in mathematics, right? Because so since 2017, I've been doing with various collaborators, just mapping out different branches of mathematics, including theoretical physics. And with my very, very talented PhD students, JK and Ellie and Ed, who we are actually working with. And soon I'm going to add Enrique and Tamas onto this list, and I think it goes under algebraic geometry. It's to appear, I don't know, in a month, 2 months, and that's with Sasaki-Einstein manifolds, which
you have to create a differential geometry blue entry.
Yes,
yes, I should to make it thicker. Yeah,
very good. I will create a new one and to appear, and I'm going to put Tamas and Enrique on, and that's also with Ellie and Ed.
Super.
So soon, stay tuned. This is an advertisement. So, of course, I'm not going to go through all of the various experiments. I'm just going to go through some speculation, because this got me really thinking about how does one actually do mathematics, right? So, one way to do mathematics is by principle. Now, this is the Principia of Russell Whitehead, right? This is when you start writing mathematics sentence by sentence, logical symbol by logical symbol. And this really started, I guess it really goes back to Leibniz and Frege, but really, certainly Russell Whitehead and Wittgenstein were thinking about this kind of problems to axiomatize mathematics. But this program was completely killed by Gödel, Church, and Turing because of undecidability. But nevertheless, I love this quote from my friend Min-Young Kim, who says the practicing mathematician doesn't think about Gödel. Because if you have to worry about Gödel, you just stop progress completely. So because of this, there's this so-called ATP program, and where people like Kevin, I'm not going to get into details of this, but people like Kevin Buzzard are really pushing forward. We're at the stage where we can write down sentence by sentence in this type theoretic language of every single step of every single theorem of every single proof, right? Every proof of every single theorem. So far, I think we have in the database everything that's undergraduate level. Standard things like Cauchy convergence to like I don't know to like prime number theorem. I think that's already in now. So this kind of mathematics, I think I want to call this bottom up because you're building mathematics bottom up, right? Now this has its own world, and I'm not going to. The approach that I'm advocating here is really not bottom up mathematics because we don't build sentences in a sense. Historically, if you really think about how mathematics is done, it's much more top down. You need some kind of intuition and experience, right, and experimentation. So I always like to use this joke, but I think I've used this joke so many times. So some of you may have even heard of this before, this joke, but for those who haven't, I love this joke. What is the best neural network of the 18th and 19th century? Well, that clearly is the brain of Gauss. Well, the brain of Gauss was able to look at this plot and say, well, this is clearly x over log x, just because you're Gauss. Maybe today, or maybe with more advanced techniques, we can do some curve fitting and say, okay, fine, this is x over log x. But the point is, this kind of experimental mathematics is where intuition and experience comes in. Now, we can do ATP by formalizing mathematics, but if you want to gain intuition and experience, the best thing to do and to use is neural networks, because that's what our brains are. We're just very complicated neural networks, which try to learn this fuzzy idea of what an intuition is. So Gauss was able to say, oh, this is clearly x over log x, even before complex analysis was invented, because that was what's required in this proof that this is true. And this happens over and over again. The Birch-Swinton-Dyer conjecture came out just simply because Birch and Swinton-Dyer in the 60s in the basement in Cambridge, they were able to plot the ranks and conductors of elliptic curves. When they plotted enough, they realized, well, oh, maybe the order of vanishing of L functions is governed by its rank. And now, of course, this is still an open conjecture. We're still waiting for the people to prove this, just like Gauss was waiting for Adamard and Delahaye-Poussin to prove this. But this kind of approach is much more amenable to what I'm trying to say here, because it is very difficult to conjecture something in mathematics now just by doing a two-dimensional plot. I think anything that involves a two-dimensional plot in any branch of mathematics has been probably done already. It's very difficult to imagine. But what machine learning is, or in fact, what the entire field of data science is good at is dimension. Right? We evolved to perceive 2 and 3 dimensions. But neural networks and any of the machine learning algorithms or PCAs, principal components, what they're really good at is to try to look for patterns in data that is higher than 3 dimensions, sometimes extremely high. And that's where we enter this world of machine learning. And this is why we were able to do so well in algebraic geometry, because the input data to this kind of stuff, once you're in dimension 4, when we think about it, you have a list of 4 vectors. So that's already some kind of a matrix or some kind of a tensor input. And that you just can't, the human eye is just, we're not trained to look for stuff like this. We're not evolved to look for something like this. But neural networks actually are. And then we can, and that's why we should do this machine learning approach to any branch of mathematics that involves dimension that's higher than 3. Even in a problem like this, when you're just trying to recognize whether a number is prime or not, you can translate this into a high dimensional vector. So here I've chosen like 100, and you're really exploring in this 100 dimensional space. Right. So to tell you some further success stories. So here's I'm just highlighting with a couple examples that's not in algebraic geometry. So here's one that was inspired with my friend Min-Young Kim, who is a very insightful number theorist. He told me to look at this problem, baby version and non-baby version. The baby version is, can you look at a Cayley table of a finite group and tell that is a finite group? So a Cayley multiplication table is a table that's labeled 1 to n and 1 to n, and then it's never repeat in any row and column. So in other words, it's a Sudoku. But of course, not every Sudoku is a proper group, because in order for a Sudoku to be a group, you have to put in associativity. So fine, but a neural network doesn't know that. So you can just put it in, and then you get very, very high efficiencies, very precision very quickly. So that's nice. So, okay, maybe your neural network is kind of recognizing like what it means to be associative. But here's something that's a much more mysterious one, which is if you plotted the Cayley table of, say, the first 1,000 groups, but enhanced with permutation, so your data size is about, say, 1 million, and then you enhance the ones that are not simple versus ones that are simple. Of course, there are much more non-simple groups than simple groups, but you enhance the ones that are non-simple. This is called data engineering. So suddenly you got 1 million or 100,000 matrices, which are n by n, and then can you recognize the ones that are simple group? Now this is crazy, right? You would never imagine that that the simple group, you're looking at these matrices, but we plotted it, and to this level of precision, a support vector machine, which is so a support vector machine is it's a machine learning algorithm, which is not a neural network, but what it does is to find hyperplane or hypersurface separators between clusters of data. It was actually able to separate this data. Now we have no idea why this is doing it, but which is great. So this is this is conjecture formulation. Now you couldn't possibly formulate this conjecture by looking, because we're looking at very, very high dimensional space. So this is where machine learning really helps us in trying to come up with what new theorems can we prove in mathematics. So this was I really like this example, because it's very high dimension, and it's something very fundamental and very concrete. And we're waiting for some very smart representation theorists to explain what is it that's making the machine do what it's actually doing. So this is one example. So in combinatorics, as another one, which is very, very much amenable to this kind of data representation. So this, I'm glad I got Yao involved in this. Yao apparently, so Yao is Yao, right? So he says, oh, I'm interested in machine learning and mathematics. So what does he do? He goes to the Chinese government. He says, I need 1 billion. And the Chinese government says, okay, when do you need it by? He says, I need it next week. That's fine. So now there's this new institute called BIMSA that's founded in Beijing, which just opened in January this year or last year, dedicated to mathematics, physics, and machine learning, to explore this kind of questions. So the experiments we did here was to just look at adjacency matrices of graphs to try to recognize whether your certain graphs are they cyclic, are they planar, and we're at this level of precision. And no, I won't bore you with quivers. So let me go back to number theory. So this is very interesting. So the example that I gave you before. So first of all, let me emphasize: if you just do blind sequence prediction, 2 goes to 3, 2, 3 to 5, 2, 3, 5 to 7, it's almost impossible to try to find a neural network that can guess this. Right? Because if I can break every bank in the world, and then I won't be here anymore. But if you feature engineer it into like a binary classifier, you get a little better. You get about 80% kind of range, prime Q tests. But this example that I said, the parity of the number of prime factors up to multiplicity is I didn't choose this example as a joke, but this is called Sarnak's challenge. And Sarnak, of course, is one of the world's leading number theorists. And he says, if you can come up with any theory that can predict the Liouville lambda function that breaks better than even, I think he'll give you some money. So I didn't get any money. But I'm not saying that there is no neural network that would do it. I'm simply saying that I couldn't find anything that could break better than a coin toss. Well, that's kind of interesting. And of course, being interested in this kind of exploration, it's natural to try to do machine learning of BSD. And here's an example that I want to emphasize, that you do need expertise. It's not like we're certainly not at the stage of mathematics where, oh, let me just going to put some random data into some machine learning algorithm and just hit return, have a couple of coffee and come back and have a conjecture. And this is a good example to show that this is not the case. We're not there yet. We probably won't be there for another century, but we might get there. So with the BSD, I mean, I'm not a number theorist, but at least I know a little bit about elliptic curves. But as I worked with some data scientists to try to learn this kind of thing, to predict rank. And we got completely random because we were feeding Weierstrass coefficients. And Weierstrass coefficients for elliptic curves of a Q are huge rational numbers. So it's kind of hopeless. So then I started talking to real, number theorists, arithmetic geometers like Qiuhong Li and Tom Oliver. And then they told me, well, you shouldn't look at Weierstrass coefficients of elliptic curves. You should look at their L function, expansion coefficients, the Euler coefficients in the L function. And then instantly you can predict rank to very, very high precision. Right? And this is nice. And so, good. I'm actually going. So, another thing to emphasize is that there's a strong version of BSD conjecture. Normally the BSD conjecture says that the order of vanishing of the L function of some elliptic curve is the rank of the elliptic curve. But there's a strong version of the BSD. They're both open. The strong version of BSD says it gives a precise formula of the rank in terms of products of very sophisticated quantities, half of which I don't understand. This is out of my field, but doesn't matter. As a data scientist, you can just try to learn these quantities. And it's interestingly that the hardest quantity, we started predicting things like integer points, torsion, whether it's complex multiplication, what the rank is, to very, very high precision. But the moment you ask what the Tate-Schafer-Average group is, the order of the Tate-Schafer-Average group is, it appears in this hard BSD, the strong BSD conjecture, which is it's the image of some very sophisticated L-adic cohomology. The machine stopped performing very well at all. I mean, it's pretty much 60%. It's not very good. And then this arithmetic geometer says, well, good, because this group is the hardest group to study. If you can crack this group, then you can really crack BSD. So in some sense, the human intuition is very much in line with machine intuition, if that means anything. So what is hard for us is hard for a machine, and this kind of idea shows over and over again. What is easy for us is easy for them in general, if you have the right data structure. So this kind of, I'm just going to sum up. So this kind of exploration is clearly great for math and physics, right? So you can look at it in two ways. One, it's very good at forming new conjectures. For example, I used the example of this separating hyperplane between simple and non-simple groups. It would be very nice for some, serious representation theories to prove that. And this has happened again in 19. My friends Brody, Konstantin, Lucas predicted an exact formula for cohomology of surfaces, which then they proved. And then we had some kind of heuristic about the distribution of L coefficients. But that, unfortunately, was already known to Sarnak, so there's nothing new. There's a new one, which we call a enumeration, which I'm not going to bore you about. And if you get a chance, please invite Tom Oliver to give a talk on that, or Qiuhong Li, which is apparently we did this kind of experiments with coefficients in L functions, and that's apparently a new one that no one's noticed before, because this kind of high dimensionality prevents human eye to detect. And of course, in 2022, there was this beautiful paper in Nature of the DeepMind collaboration, where they started conjecturing volume bounds for knots. So machine learning, this top-down mathematics as a tool for conjecture formulation is clearly useful. Another thing I want to emphasize that it's clearly also useful for speeding up computation. So here's an example that I tried with Ashmore and Overroot about 3 years ago, which I think Enrique would be interested in. There is, because I think Enrique was Donaldson's son, or intellectually. So I mentioned this thing about Claviel. There is no known non-trivial analytic Claviel Ricci flat metric. We know there are all these Claviels, right? We've given you 500 million, but nobody knows of on a single one of them what is the explicit analytic expression for metric. Because Yale's proof was a non-constructive one. But nevertheless, Donaldson came up with an algorithm about 10 years ago, which numerically shows how you can converge towards this metric. So he uses some kind of which he called a T operator, which you can iterate to hit on the basis of polynomials, which converges very fast. It's sort of an extension of the Fubini study, generalization of the Fubini study to this Claviel. So that's very nice, but again, you can imagine it's a very expensive numerical computation. So we took part.
Can I just say this? So this is known in geometry as the Donaldson sequence of balanced metrics, right? So it's how do you find the exact Ricci flat representative within a given Kähler class? And there's a mathematically proven way to achieve it. And these folks tried to implement it numerically and found that it's numerically very expensive. And then these AI guys came in and ML'd this into a huge efficiency. And your student, Ellie Hayes, is looking at this in the G2 context with us. So yes,
exactly,
very much.
Exactly. Which is in some sense surprising because we use a very simple feed-forward neural network, and that was able to speed up Donaldson by almost 2 orders of magnitude without knowing anything about balanced metrics. But that's the good thing about this new neural network. It doesn't know what it's doing, but all it's doing is feature recognition, right? It's somehow figured out there's a cluster of patch that it kind of optimizes over some kind of metric. Let's just try to converge towards that. So it's faster than if you just actually try to create this monomial basis for the balanced metric. So at least I can see at least 2 reasons why you should do machine learning assisted mathematics. You can look for new conjectures, and it will speed up computations for you. So it's a win-win situation. So and something that I've been trying to speculate, do the accuracies performed by the machine learning algorithms also show some kind of inherent hierarchy in mathematics? Numerical analysis is always really good with machine learning, and analytic number theory is always really hard. This is true to some degree, as from experience. And luckily, algebraic geometry or arithmetic geometry are closer to numerical analysis than they are to analytic number theory. So, and for machines, that is also the case. There is a new journal. Ignore the name of who the editor is, but I think it's a wonderful journal that's just launched this year. And if you want to explore this kind of stuff, I highly encourage you to submit to this journal. And I think, I can stop here now to take questions, or I can go on a little bit more about meta mathematics if you wish. So up to you.
All right, so let's thank Yang again within time, and then we can proceed to questions. Thank you. Yeah, my dog was actually startled with all the clapping. I should do this from my office. Yeah, she just woke up. Yeah.
How big can we see the dog?
Yeah, it's down there. There she is. She was startled by it. Anyway, so what about, so do we have questions for Yang? He can expand on some of the things he outlined. I know he talked mostly about like number theory stuff, but within the geometry community, we can certainly find proto problems that look like this. And this was my idea here. Yang and I have been collaborating on things like Sasaki and Hodge, predicting Sasaki and Hodge numbers from these polynomials and so on. Also trying to implement Donaldson sequence to get G2 sort of solutions to the G2 heterotic system. But surely some of you can think of similar problems for which data sets can be generated. So the floor is open. Do we have even tentative questions, risk-taking questions? Give it a shot. You can raise your hand by the handy little thingy, or you can just switch on the mic. Carlos.
So I'm kind of lost in this question of the Ricci flat matrix. There is an algorithm to that converges to a certain metric, but it's very expensive numerically, and then there's a way to bypass this difficulty using ML. Is that the case?
Yeah, this is one. So that's what we did, was to sample. What we did was to do. I mean, it was very naive, and I'll mention this later work in a minute. But we just sampled bits that were created by the regular Donaldson algorithm, because the way the Donaldson algorithm works is that you go higher and higher in degree, and once you go higher in degree, there's a bigger and bigger monomial basis, and then you can do the Donaldson T operator, and then you get some kind of one level of convergence. So now what we did was to use the Donaldson to sample a small sample of points to some patches, and then use that to extrapolate over the entire patch.
You mean you constructed something locally?
Yes, absolutely. Yeah.
And then used it to train a certain ML algorithm.
Yeah. So but I should also emphasize that then what these guys did, Douglas and collaborators and Anderson collaborators, what they did was to completely forget about Donaldson, forget about convergence of this Donaldson balance metric. They literally set up a loss function, a loss function which is it's clear what the loss function is. You have a metric, you compute the Ricci tensor, and you do the integral of that over a patch. And then you create a neural network whose loss function is this, and they use activation functions which are polynomial activation functions. And then it started to converge patch by patch into something that really extremized. So that doesn't even use Donaldson at all. So, and that was also much quicker.
And how deep is the network to it?
It wasn't deep. I mean, in fact, you can if you look for Douglas, if you can Google on GitHub, they have put their all of their thing in PyTorch on GitHub, so you can play with it. It's very we used Mathematica, because I was very naive into this field, but the Douglas one is on GitHub in PyTorch, and it's not deep at all. It's maybe like I don't know, 5 or 6 layers or something. It wasn't very complicated, and it's already doing so well.
Amazing. Yeah, thanks.
Let me say one more thing about it, Carlos, because I think you're gonna like it. So you may think this is all like some sort of local cheat, and that the model would completely fail to understand global structures and global phenomena. I know that because that's what I would think 2 years ago.
Sure.
No, that's really not the case.
Yeah.
It really understands global tensors and geometric structures in a very interesting way. So you want to plot tensor-like objects on each coordinate path, and then the compatibility condition itself, right, that it transforms as a tensor when you change from a patch to the other, that's built into the loss function you want to optimize. Right? So you literally do T minus the conjugate action of of your change of charts on the original tensor, and which you would like to be 0, right? So you would like it to transform perfectly, but then you just pose the failure to transform perfectly as a term to be minimized within the loss function. And what's going to do is to find things that are almost transform like tensors, but try and make them transform as tensors as closely as it possibly can.
As close as possible. Yeah.
Yeah. Right. It's fascinating. You just add.
Yeah, and once you have this loss function, it's just a regular neural network with,
well, it's
I
just
don't know, with
gradients.
usual activation functions and.
Once you have a loss function, is gradient descent mostly, but then.
Right, I see.
Yeah, it is doable. But geometric structures can be encoded like this.
And it efficiently finds a local minimum of the loss function, because I know that that's the that's
yes,
the problem,
that's right.
To do that in a reasonable amount of time.
Yeah. One unusual thing that Douglas tried is not to use, the standard activation function for each neuron. Normally, you use things like hyperbolic tangent, but they found the ones that really did well were polynomial activation functions, which is a bit strange. Normally, you don't use polynomial, but it's because there's an algebraic structure. So that was a very novel idea there to use polynomial.
But activation functions are smooth in this case. Not like
it is with an interval. Yeah, that's right. But it doesn't have to be. Activation
it doesn't have to be, and it's good that it's not usually.
Yeah, that's right.
Things like relux and.
That's right. I suspect if you use like piecewise linear, everybody's favorite like ReLU activation, then you probably need a deeper network to do it. But you will do it. You will find something that will work. That's the magic about under the hood. I mean, you will never get an analytic result out of it. But if you want a numerical thing, your neural networks will find it.
No, it's amazing. Yeah,
it is amazing.
Yeah, thanks.
Sure.
Any further questions? Well, if not, then let's thank Yang again.
Thank you for having me. And hopefully the paper with Enrique and Tomasz will be out soon, and then at some point I can go and see you guys in person.
Excellent. Yeah, by all means. Let's try and do this by the end of the year. Cheers, Yang. Thank you so much.
Thank you so much.